Good day to each and everyone. Today we're going to talk about the conservation of angular momentum. So what is angular momentum? Angular momentum is a measure of an object tendency to continue rotating or revolving around the center axis dependent on its mass, velocity, and distance from the axis. How is angular momentum different from linear momentum? Remember, angular momentum is due to rotation. In this lesson, we'll derive and discuss the angular momentum equation for a fixed control volume. We'll look at the various moments acting on a control volume and do an example problem as we did with other conservation law. We start with the Reynolds transform theorem for a fixed control volume. Remember, this is our link between the system and the control volume here. We let capital B, BH, and the angular momentum vector, which is some moment arm R cross product with MB, where B is the velocity vector, little b is always B over M. So that's just R cross B. The result is given here, where we'll put the relative velocity here just in case you want to do some moving control volume problems, but those are beyond the scope of this lesson. Let's look at the terms. This first term is the sum of all external moments acting on a control volume. The second term is the time rate of change of the angular momentum of all the contents within the control volume. And the third term is the net flow rate of angular momentum out of the control volume surface by mass flow, as we did previously for mass, energy, and momentum. We simplify this term for well-defined inlets and outlets. I'll drop the subscript R. We're also considering only fixed control from now on. Here's the result. Second term is the same, but the third term here is written as summation over outlet minus inlets, as I pointed out previously. Signs takes of themselves at outlets B and N are nearly in the same direction, and therefore these are positive terms, and that inlets their negative terms. Unlike the previous cases, we can't really define an angular momentum flux correction factor. That's because in general we're taking a moment about some point, so we draw the moment arm vector R. We have to take the cross product of that with M dot B. Usually the cross-sectional length or diameter of this outlet is small compared to R and A. Correction factor would have to include R through this integrated, which would get very complicated and be different for every problem. So we're just going to ignore any kind of correction factor here. I've leveled the term. This is the net moment or torque act on the control volume by external means. This is the rate of flow of angular momentum out of the control volume by mass flow. This is the same thing, but control volume. At inlet, we also drop unsteady term. We'll only consider the steady problems here. For further simplification, we're generally talking about moments in one place, in this case around the axis, that point out of the page, so we can turn this into a scalar equation. When we're analyzing about this axis, R cross M dot B will also be a moment about that same axis, so the scalar equation becomes sigma M equals to sigma out Rm dot B minus sigma N Rm dot B. This is our most useful or workhorse equation for angular momentum type problem. As I showed here, R is the shortest distance or the distance at 90 degrees to the outlet or inlet velocity vector. The sum holds true for forces by convention. Counterclockwise moment are positive using the right hand rule, where in this plane of the page, counterclockwise moments about that point or line coming out of the page are positive. Let's do one simple example. This is example 6a. We have water coming from underground through a pipe, an elbow and an extension, and the flow comes out horizontally. We give some dimensions and weight. This pipe is anchored to this concrete base. We want to calculate the bending moment acting at the base of the pipe, which is point A. Here are our assumptions. Approximation: the flow is steady. Since this is a jet exiting into the air, the gauge pressure at the outlet of the zero of the pipe diameter is small compared to the moment arms, so we can just use average values of radius and velocity. At the outlet, first we pick a control volume. Wise control volume would cut through that point where we want to find the moment, and we got along the outside of the pipe cutting through the outlet. Since this pressure is atmospheric, we don't need to consider pressure course. They all cancel out. Another way of thinking of this is to do everything in terms of gauge pressure, and then the pressure around this entire control volume is zero. In the term terms of gauge pressure except for this pressure P sub 1, but that does not contribute to any kind of a moment around point A. We calculate the mass flow rate raw cross-sectional areas times B. We get our results in kilogram per second. We were given the weight of the water at the pipe per meter, so we calculated this total weight which acts at a distance of R1. From the center line of this vertical pipe, if this pipe were longer, W would act further to the right. Here's our result in the newtons. We use our workhorse equation to find MA. This sigma M term on the left represents moments acting on controlled volume that would include moment caused by this weight. For example, the term on the right are moments due to angular momentum. Probably the most difficult part of this kind of problems is getting the sign correct at an outlet. There's only one inlet, but since point A is in the middle of that, it contributes nothing to this moment, so that term goes away. There is an outlet with some M dot and some B and a moment arm R to about point A. Since it's an outlet, this is positive in this case. In the clockwise directions, we include a negative sign here since all our moments are considered positive. Counterclockwise again, this is the most difficult part of the problems, getting the sign correct. We know intuitively that this jet is going to cause a counterclockwise sign. Counterclockwise moment on this pipe about point A, but the actual angular momentum flow rate out of the control volume is in the clockwise direction, which means we need a negative sign in our equation, which deals with counterclockwise moments as positive. Putting it all together, we get this equation M A minus R on 1 R1 W equal minus R2 M dot B. To the rest of the problem is just solving for MA from here. We get MA equals R1 W minus R2 M dot B. 2 we plug in the numbers and get our answers from MA and note that it's negative, which means our assumed direction for moment MA, which was counterclockwise or positive, mathematically was incorrect. The actual moment is clockwise, implying that in the tug of war between this weight causing a clockwise moment and this jet causing a counterclockwise moment on the pipe of the jet wins because the sign can get confusing. I recommend writing the answer as MA equals 82.5 Newton meter clockwise. This moment is acting on the pipe. In other words, the concrete base must apply a clockwise moment on the pipe at the excess moment caused by the exit stream. Finally, since to counter the weight in the moment are kind of fighting each other, there will be a weight pipe where each moment will just balance the moment of the jet. We want to find that weight such that in other words, there's no net moment. MA would be 0 at the base of this pipe. We want to solve for length L of the horizontal pipe that cause that moment to vanish. We use the same equation here but set MA equation 0 and we solve for length L. Plugging in the number we get 1.55 meter. Going back to the diagram, we see that by making this horizontal length of pipe longer, the moment arm of the weight moment is increased, and the calculated length, the counterclockwise moment caused by this set, and this moment arm will be balanced by the weight in this moment arm, rendering MA 0.